Welcome to the next session on real numbers, session 3. Today we are going to study more about Euclid's division lemma and its applications. Okay. Now in the last session I had given you a puzzle. Many of you had given the correct answer. Anyway, I am going to tell the answer how it is. Now 119, if I divide by 1, obviously no remainder. If I divide by 2, I will get the remainder as 1. How? 59 times. And then this is divided by 3. You will get 39 times. 117. Remainder is 2. And if I divide this by 4, the remainder is 116. It can be divided. It is 29 times. Isn't it? So the remainder is 3. Then 119, you are dividing by 5. 23 times. 115 and the remainder is 4. If I divide by 119 by 6, you will get 2, 1, 6 are 6 and 559 and then 19 times. Isn't it? 19. 1 times, so it is 19, remainder is 5. Now what about this 119 is divided by 7? So you are able to divide it, 1 7s are and then 4 and 17 times. So remainder is 0. That is, and moreover this number is less than 150. So the basket cannot hold more than 150 makes sense. So this is how you should find out. How did you do it? Simply by trial and error and also application of your LCM. Okay, this is how you have to get this answer. So like that, many interesting puzzles you also can create. Only thing is you have to work on that and then design a suitable puzzle and send it to me. I would really love to see your responses. Okay, now we'll move further in this chapter. We studied in the last session, any number can be written in the form, any number A, any positive integer A can be written in the form BQ plus R, where R is between 0 and B. This is what we studied that is, it doesn't have any limitation. It can go even beyond greater than this also, the divisor also, that is namely the B. And we also brought the analogy between the division algorithm and Euclid's division lemma, that A is the dividend and B is the number that is going to divide, which is the divisor, and Q is the quotient, that is how many number of times that B divides A, and R is the remainder. So if you are able to fit both, it is one and the same. Okay, this is what we studied. It goes up to infinity. So if that is the case, in order to prove this result, we are going to take some number. We are not going to analyze whether it is even or odd. We are going to represent any number in the form, any number. It can be A or B or you may call it any name. It can be written in the form 2Q plus R, where R is less than or equal to 0 is less than or equal to, and then here the number is 2, so this is the thing. Are you understanding? So when you are able to write instead of B, I have put 2. That is, any number can be written as a multiple of 2 plus some remainder. Are you understanding? That is the meaning of this statement. Is it clear to you? That is, B can take any value, isn't it? So that means now I have given the value of 2. Any number can be written as a multiple of 2 plus some remainder, R. Now when we are writing it as a multiple of 2, the probable values of R will be 0, 1, only 2 cases. Will 2 come? Well, 2 comes means it becomes only 2Q, 2 times that number. So that cases are only 0 and 1. Are you understanding clearly? Okay, now here when we are writing it as a multiple of 2, the limitations for R is only 0 and 1. It can either take the value 0 or it can take the value 1. Is that clear to you? This is our first assumption. Is that clear to you? Now let us analyze the case. Any number, suppose for example, one A you have already taken. So I write a is equal to 2q plus 0 when r is equal to 0. So let us analyze this case 1 as r equal to 0. What will happen? You will get any number a is equal to 2q plus 0, that is a is equal to 2 times q. When we say a is 2q means a is a multiple of 2. A is an even number. Correct? Otherwise we can't get it. No, 2 times a number is obviously an even number. Correct? So any even number can be written as 2 times some number. Are you understanding? So this answers the first question. Every positive integer, any positive integer can be written in the form 2q provided it is an even integer. So therefore this gives the result that any even integer can be written in the form 2q. Correct? Now we have to analyze the case. So we can write a is an even number. A is an even number. Now when r is equal to 1, what will happen? We will get a is equal to 2q plus 1. That means what? We are able to write a number a 2 times the number, 2 times some other number, and the remainder is only 1. That means it should be an odd number. Correct? So a, when we are able to write it in the form 2q plus 1, the remainder is 1 obviously states that the number is an odd number. We are able to write that number a as 2 times some other number plus the remainder 1. Therefore, in this case we can write a is equal to a is an odd number. So that's generalized the result that any odd number can be written in the form 2q plus 1 and any even number can be written in the form 2q. Is a very fundamental question that you all should know. With that knowledge only we have to go further. Move on to the next sum, children. Continuing in the same pattern, we have got one more sum. Any positive odd integer is of the form 4q plus 1 or 4q plus 3 where q is some integer. Okay, so what have I told you? Continuing in the same assumption, any integer, okay, or any positive odd integer, or we can take any integer itself we can take. From there we can generalize the case for odd integers. Okay, so any integer can be written in the form 4q plus r, where this 4 is the divisor and q is the number of times it divides and r is the remainder. So this is, then r has got the limitations as it can take the value 0, 1, 2 and 3. Only these 4 values r can take. Are you understanding? So any integer can be written in this form. Okay, so if that is the case, what is happening to the odd integers? That's what we are going to see. We are not taking the odd integer is of the form we are not taking. We are taking as any integer of the form 4q plus r. In 4 cases we are going to analyze. In what all cases we are going to get this form is our prime area. Okay, please listen. Now any integer a can be written in this form. Okay, so if that is the case, there are 4 cases. First, let us analyze what will happen for case 1 when r is 0. If r is 0, you will get a is equal to 4q. A is 4q means what? It is 2 times some value, isn't it? 4 itself is a multiple of 2. We are going to break it into further 2 into 2. That is, we can write this as 2 into 2q, or we can write this as 2 into some number of times. Only this number will respond. There is no remainder. Correct? Therefore, this has to be what? It is an even number. It is an even number. So, we are not going to consider this case. Correct? Are you understanding? Now, let us say what is case 2. Examine what will happen when r is equal to 1. If r equal to 1 means your a will become 4q plus 1. So when it is 4q plus 1 means what do you understand from this? This 4q alone can be broken up as 2 into 2q plus 1, or we will be able to write this as 2 times some number, correct, plus 1. Is it understood clearly? This is very, very important. 2 into 2. So you can even try to fit in with some numbers. For q plus 1 you take, for example, 17. 17 is what? 4 into 4 times plus 1 remainder, and that is nothing but 2 into 8. Isn't it? That means we are able to write as a multiple of 2 plus 1 remainder. In that case, it is an odd number. This is an odd positive integer. Correct? Now, what will happen to 2? Let us see. So, case 3 analyzes r is equal to 2. When r equal to 2, a will become 4q plus 2. That means 2 into some 2q, multiple number of times, plus 1 more 2. We can take the 2 as common, and the whole thing can be written as 2q plus 1. That is, the whole number can be written as 2 times some number. Correct? 2 I am taking it out. So 2q plus 2. So that will become 2 into 2q plus 1. 2 times some number. That means this is also even. Let us take the fourth case. Case 4. So in the case 4, what will happen? R is equal to 3. If R equal to 3, A will become 4q plus 3. Correct? Now, how are we going to write? This 3 can be splitted as 4q plus 2 plus 1. Yes? Now, this 4q plus 2 can again be written as 2 into 2q plus 2. I can bracket together like this. And then I can write 2 times some multiple. 2 times, I can take it out like this. 2 times some multiple of 2 plus 1. So 2 times a number plus 1. So even that 4q plus 3 can be written as 2 times some number plus 1. Therefore, in this case, what will you get? You will get an odd positive integer. You will get odd positive integer. Now, I want you to once again examine all the 4 results. When r is equal to 0, you got an even number. When r equal to 1, it is reduced to the form 2q plus 1, we get an odd number. When r equal to 2, the whole thing gets reduced to 2 times a number, that becomes an even number. When r equal to 3, a becomes 4q plus 3. Finally, that also gets reduced to the form 2m plus 1. Therefore, in all the 4 cases, what do we see? When it is any odd number, will be of the form, any odd positive integer will be of the form 4q plus 1 or 4q plus 3. That is the conclusion. We have to write here. Therefore, any odd integer, after analyzing these 4 cases, any odd positive integer will be of the form 4q plus 1 or 4q plus 3. So this is very, very important, that the result we have got. Now, let us move on to the next section. So this is probably the third sum. Find the HCF of 185 and 75. So this is nothing but the same thing as you studied in your lower classes, maybe 6th or 5th you had studied that. Again, we are going to study that in the new format. That's all. That's the only difference. So what you used to do? You do by continued division method, or you will do by prime factorization method. There are 2-3 methods available for that. Now I am going to teach you how to do using Euclid's division lemma. It is more the same thing as you studied as continued division method. Okay, there is nothing, no difference in that, but we will be able to fit in the new format. That's all. Okay, so using continued division method. So I will write it here, 75 and then 185. You are able to divide it 2 times. So it is 150. The remainder is 35. Again this remainder is going to divide 75. We are able to divide it 2 times and then the remainder is 5, and this remainder is going to divide this divisor. So you will get 7 5s are 35. The divisor which made the remainder 0 is the HCF. This is what I have taught you in your earlier class. Here also you are going to do the same thing, the same steps. But here you cannot leave the answer in this format. We have to use your Euclid's division lemma. How will you use it? Originally, what did we do? We have divided 185, sorry. So 185 is the dividend. It is divided by 75, which is the divisor. How many number of times? 2 times you have divided. And what is the remainder? 35. So this is the first step, and here we are applying lemma, Euclid's division lemma statement. Are you understanding? Now, then what did we do? We are dividing the 75 by what? By this 35. Why? That is the next number. Okay, so we are going to divide the previous divisor. You can even say next is we are going to divide 75 by the divisor 35, and 2 times we are dividing, and obviously 5 is the remainder. So this we are applying directly the lemma. Okay, Euclid's division lemma. Now what did we do? We are dividing this 35 by which number? The remainder. Therefore, 35 is divided by 35 is equal 5 divided by 5. How many times? 7 times we are dividing, and what is the remainder? 0. Now the divisor which gives a 0 remainder is the HCF. Circle it and write HCF is equal to 5. This is your answer. Are you getting it? Once again I will repeat the steps. We are just dividing by continued division method, which you studied in your earlier class. How to do continued division method? The smaller number you should take it in the divisor's place and divide 185 by the smaller number. Obviously we are dividing by 2 times, and then 35 is the remainder. Now this 35 has to divide the divisor, the 75 previous divisor. That again divides it 2 times, and then the remainder is 5, and this divisor is going to divide the previous divisor, that is 35 7 times, and the remainder is 0. Now this particular division has given you the remainder 0, therefore 5 is taken to be the HCF of the 2 numbers. Now we are applying the same division method, continued division method in this. How are we doing? So 185 is divided by 75 2 times, and remainder 35. Same way this 75 is divided by 35 2 times, and the remainder is 5. And then this 35 is divided by 5 7 times, and the remainder is 0. And just because the remainder 0 means the particular divisor 5 is the HCF. Are you understanding? This is how we will find the HCF of the 2 numbers. Okay. Following the same principles, I am going to do a small homework, and this is from exercise 1.1, sum number 1. Sum number 1, there are 3 subdivisions. You have to find the HCF of the following, obviously by Euclid's division lemma. Okay, 135 and 225, 196 and 38,220, 867 and 255, which we will be, I just want you to work it out and come with the answers for the next session. Till then, wish you all the best. Thank you, children.